Okay, all right. So this is the recording for the class today, November 10th, all right, concerning lipids. And so what I suggest you do is I'll talk through all of these and the different potential answers and the correct answer. So what you can do is between each question, I'll stop so you can hit pause on the recording so you can try to answer the question yourself. And then after you answer the question, you can then just press play to hear the discussion about the correct answer, okay? All right, so the first problem you see on the screen says saturated fatty acids are different to unsaturated fatty acids because they blank. And so one thing that gives you some background about this is butter is composed largely of saturated fatty acids versus vegetable oils are composed largely of unsaturated fatty acids. So using that information as some background that might help you in this, try to answer the question. So please pause the recording now. Oops, that's not what I meant to do. It's the okay. And so the correct answer, of course, is C. They have no CC double bonds. Okay, so remember the difference between saturated and unsaturated fatty acids are that saturated fatty acids have all single bonds within the chain. Okay, so another way to think about this is that all the carbons within the chain, right, of the nonpolar tail, right, are saturated with hydrogens. So that's the kind of context of what saturated versus unsaturated means. Versus when there's a CC double bond, right, some of the carbons have less hydrogens due to the fact that they have double bonds and therefore what we call unsaturations, okay? And so how this relates, again, towards this, what we're talking about with butter and vegetable oils is with saturated fatty acids, right? The chains, the fatty acid chain is free to move, okay? But when it packs together with other saturated fatty acids, right? The conformation of lowest energy is to have the chains completely almost what you would think about as straight, right? So that they increase the number of contacts with each other. And so what happens is these pack in a way, okay? And because they pack, what they do is they pack really tightly and they're more likely to be solid at room temperature, much like butter, okay? And so because butter is composed largely of saturated fatty acids, that can account for its solid, the fact that it's solid at room temperature versus at room temperature, vegetable oils are liquid, and that's because there are more unsaturated fatty acids. And so it may not be totally clear why that might happen, but if you think about the least energy conformation when packed, right, for saturated fatty acids being a straight line, if you put a double bond, and more importantly, if you put a cis double bond, right, since all double bonds, biological double bonds in these unsaturated fatty acids are in the cis conformation, right, what happens is it causes a kink in the tail. And so it causes it to create an angle. And so what that means is that this one lipid that has an unsaturation, it can't pack very closely with neighboring lipids. So it has more space in between it. So let's go to the whiteboard to show this a little bit more clearly. Okay, click canvas. All right. Okay. So again, let's say we the whiteboard up. Let's say we denote a fatty acid as this being the polar head group. And this being the nonpolar tail. Okay. So again, for saturated fatty acids, when there are a lot of them packed together, right, that tail is going to be fully extended to increase the number of energetically favorable interactions between the hydrophobic tails, right? And they're going to be very closely packed. Now, for an unsaturated fatty acid that has a double bond, it's going to look a little different. So we still have the polar head group, and then you may have some of the tail, but then because of the double bond, it causes a kink, right, in the tail, all right? So imagine putting one of those inside of here, right? And what you would see right, is that it causes lipids surrounding it to require more space, right, through steric interactions, right? So those neighboring lipids can't necessarily get as close in contact to that because of that bend in the chain. And so what that means then is that since they can't pack as closely, right, they're more likely to be more fluid at room temperature. And so this affects the melting temperature. What we talk about is the melting temperature, right, of the I guess the lipids packed on each other, okay? And that will affect ultimately when we talk about membrane fluidity, okay? All right, let me change back to the PowerPoint. All right, and so for that reason, so in other words, butter has a higher melting temperature than vegetable oils, okay? And again, that's because the butter has a higher composition of saturated fatty acids and is able to pack easier, okay? Versus the vegetable oils, which has a higher composition of unsaturated fatty acids, and therefore the melting temperature is much lower, okay? Here's our compositions, okay? For your reference. So there's our butter. Saturated fat is 7 grams, the 11 grams of fat. And then unsaturated, and then for vegetable oils, 12 of the 12 grams out of the 14 total grams in a serving of vegetable oil are unsaturated fats. Okay. So this question reads, in an aqueous environment, the hydrocarbon tails of lipids tend to associate by entropy-driven blank and by van der Waals interactions. Pause the video now to try to answer on your own and start when you're ready. Okay, and so this is a classic case of the hydrophobic effect, or B, okay? So this is similar to what we talked about, the hydrophobic effect, when we talked about the formation of tertiary structure and quaternary structure of proteins, okay? And also the formation of micelles. All right. Next question is, which of the following statements about the fatty acid shown below is true? A, it is saturated. B, it forms a bilayer when mixed with water. C, it is a component of membrane lipids. D, it is amphiphilic. Or E, both C and D are true. Pause the video now to try to answer on your own. The correct answer here is E. both C and D are true. Okay, as we can see, we have an unsaturation in the fatty acid. We have a double bond, so A is false. B, it says it forms a bilayer when mixed with water. However, we know that from the videos, right, that the bilayer, right, whether an amphiphilic molecule forms a bilayer or micelle is dependent on the relative size of the head group versus the hydrophobic tails. Okay, and so for most fatty acids, the head group is too small in order to form a bilayer, and instead something like this, when mixed with water, will form a micelle. So B is false. C, it is a component of membrane lipids. It certainly is a component of membrane lipids, and that is true. And then D, it is amphiphilic. It is. It has a polar head group and a nonpolar tail. Right? And that is what we expect for an amphiphilic molecule. So our correct answer is D. Both C and D are true. Next question is, why are glycerophospholipids capable of spontaneously assembling into the bilayer structure found in biological membranes, but triacylglycerols are not? Okay, here's a picture of a triacylglycerol. Okay, so is it A, glycerophospholipids are amphipathic and aggregate into bilayers that can interact with water on both faces? Is it B, triacylglycerols have 3 acyl chains that do not align easily side by side to form a bilayer? C, that triacylglycerols are not amphiphilic? D, both A and B are true? Or E, A, B, and C are true? Pause the video now and return when you have given it a chance. Okay, the correct answer here is E, A, B, and C are true. Okay, so A, glycerophospholipids are amphipathic and aggregate into bilayers that can interact with water in both faces. This is correct because there's a polar head group on glycerophospholipids. If you look at the structure, and of course the nonpolar tails of the 2 acylated fatty acids on the glycerophospholipid. Okay, so this is correct. For B, triacylglycerols have 3 acyl side chains that do not align easily side by side to form a bilayer. Yes, this is also correct. Okay. And then C, triacylglycerols are not amphiphilic. Right? And so if you look at the structure of a triacylglycerol, such as the one shown on the right, okay, you see, of course, the nonpolar tail. But if you look at the head group, right, those are not terribly polar either, right? That's a glycerol. They're not charged, okay? There aren't because they're stuck in an ester instead of a carboxylic acid, and there aren't any charged groups. This is also fairly nonpolar, okay? So these are also not amphiphilic, okay? So all of A, B, and C are true. Okay, the next question is, can a pure sample of cholesterol form an artificial bilayer when mixed with water? Is the answer A, yes, as cholesterol is weakly amphiphilic? B, yes, as cholesterol is amphipathic and has the correct shape for close packing? Or C, no, as cholesterol is almost entirely hydrophobic? Go ahead and pause and then come back when you're ready. Okay, so the answer to this is C. Oops. For a second. C. No, as cholesterol is almost entirely hydrophobic. If you look at the molecule, you may see the OH group here and think of that as a polar. But if you look at the large majority of the rest of the molecule, it almost doesn't matter. It basically doesn't matter much at all. That you have that one small polar functional group there. And so this molecule is largely non-polar and wouldn't be considered amphipathic. So cholesterol cannot form a bilayer when mixed with water, right? Okay. So when we talk about integral membrane proteins, right, we're thinking about often these integral membrane proteins will have alpha helices associated with them. So in the membrane, in the lipid bilayer of the membrane, not only do we have the lipids that we were talking about, right, that help to compose the lipid bilayer, and of course the structure of what those lipids are that are contained are important for making sure this is a lipid bilayer versus a micelle, right? And then in addition, the composition of the fatty acid chains that are composed in these larger lipid structures, such as glycerophospholipids, right, are important for maintaining the melting temperature of the bilayer and control the fluidity of the bilayer. Okay, and so these constitute the outside of the cell, right? And so they act as sort of this initial barrier, right, to control access of the inside of the cell to different molecules or ions that are critically important for the function of the cell. But of course, there needs to be a way to transport across the for instance, transport across the membrane and do other functions that are required at the surface of the membrane or within the membrane, within the lipid bilayer. Okay, so there are a vast number of different types of other biomolecules incorporated, including several proteins, all right? And so we have different types, such as a peripheral protein. We have integral membrane proteins, which span the entire membrane. And then here's another type of integral protein. And we see that there's a hydrophobic, a single alpha helix that spans the lipid bilayer. Okay, and we'll talk more about the different types of proteins later. But right now what we want to look at is the helix structure and why that's important for transmembrane, what are called transmembrane domains. That is, the domains that allow the protein to span the lipid bilayer and be incorporated inside the lipid bilayer. Okay, so let's take a look at the alpha helix structure and the beta sheet to look at the differences. So with the interaction between the side chains of a polypeptide and a non-polar fatty acid tail inside the lipid bilayer be energetically favorable or unfavorable? Go ahead and pause to answer the question, and we'll come right back. Okay, so the important things here are side chains of a polypeptide and non-polar fatty acid tail inside a bilayer are favorable or unfavorable. And of course, if we're just talking about the side chains, right, it depends on what the side chain is, right? So we're thinking C, right? So if that's a charged group, such as from an aspartate or a glutamate residue or an arginine residue, right, you wouldn't expect that to be very favorable within the context of a lipid bilayer, right? Because a charged molecule is not going to a charged molecule interacting with the non-polar region of the lipid bilayer is not energetically favorable. However, for instance, isoleucine might be right at home inside of the lipid bilayer because it is also a non-polar side chain, right? And so the side chains could provide some context into what, how these structures or what amino acids, right, there are in the transmembrane domain. Okay, so now let's consider this from a different angle. So not just the side chains, but other things that are common with the polypeptide. So what about the interaction between the polar groups in the peptide bond and the nonpolar fatty acid. Would that be energetically favorable or unfavorable? Go ahead and pause your video to try to answer and think about it, and then come back when you're ready. Okay, so we know that the peptide bond, right, is polar. So polar interacting with the nonpolar fatty acid tail or the nonpolar region of a lipid bilayer would be unfavorable, right? So we know that. Okay, so how do we get around that? So why are alpha helices preferable to beta sheets for transmembrane domains? So pause the video now and take a couple minutes to take a look at these two images of the beta sheet and the alpha helix and see if you can come up with some reasons structurally why an alpha helix might be more favorable as a transmembrane domain versus beta sheet. So here are some choices for you to think about. Is it A, alpha helices hide the side chains from the nonpolar interior of the lipid bilayer better? B, alpha helices hide the polar functional groups of the peptide backbone from the nonpolar interior of the lipid bilayer better? Or C, alpha helices look cooler? Go ahead and pause, consider your answer, and then come back when you're ready. Okay, so let's go through these. So obviously alpha C is completely your preference. Which one you think looks cooler has very little to do with which one's better for going through the membrane. So we'll go ahead and cross that out. But A, right, alpha helices, right, the side chains, if a single helix goes through the integral membrane protein, right, the residues are going to be like spokes around a hub, okay? And so that means they will point out, just like we discussed before, from the, right, so where these purple spheres are, right, there it is. These purple spheres are on this diagram, right, they're gonna stick out towards the outside, right? So the alpha helices really don't hide the side chains at all, okay, to lipid bilayer. So it's important that the side chain residues that compose the alpha helix that's going through a lipid bilayer are compatible with the hydrophobicity of the lipid bilayer, okay? So by process of elimination, B is correct, right? But let's talk about that a bit more in depth. So alpha helices hide the polar functional groups of the peptide backbone from the nonpolar interior of the lipid bilayer better, right? So if you look at the structure, right, of the alpha helix, let's look at our peptide bonds, right? So we were talking about how peptide bonds interacting with the nonpolar tails, right, would be energetically unfavorable. But let's take a look at where those peptide bonds are. So let's just take a look at these three. For instance, and then the other one is out here, okay? So notice how in the alpha helix, they hydrogen bond with each other, okay? Right? And so what that does is that means the CO and NH groups are in plane with the outer barrel, right? With the helix, right? Like the exterior wall of the helix, right? And so what they're doing essentially is keeping from the polar NH groups, right, and the polar CO groups from sticking out into the nonpolar, into the hydrophobic region of the lipid bilayer. Because if they stick out like that, then that dipole, right, that permanent dipole is then pointing into the nonpolar region, and that's energetically unfavorable. But if they're parallel to each other, two things happen. One, they're not really interacting, right? That dipole, right, is not interacting with the hydrophobic tails of the lipid. And another, the hydrogen bond, right, kind of sequesters these two dipoles and sort of neutralizes them. So in effect, they're kind of they're somewhat more they're somewhat less polar than they would be on their own. Okay, and so that allows for the alpha helix to be a really good structure for going through the lipid bilayer, the nonpolar region of the lipid bilayer. By contrast, right, the beta sheets, right, if you take a look at these, right, the beta sheets have to end at some point. So if we just say this is the edge of our beta sheet here, right, and then we have, let's say we have, this is a larger structure like this, right, like a you have three sort of chains involved in the beta sheet, right? And so if this is the edge, right, and this is pointing out to the hydrophobic region, right? What is pointing out to the hydrophobic region? Well, these NH and CO groups, right? All these dipoles, right, are pointing towards the hydrophobic region, which, as we said, is not energetically favorable. Okay, and so beta sheets have a hard time of acting as transmembrane domains, although that's not to say that they cannot be involved in some way in membrane proteins, which we'll discuss more in our next module, but they're not typically involved in the transmembrane domain, that is the region that spans the lipid bilayer, the nonpolar region of the lipid bilayer. Okay, using the figure below to estimate the number of polypeptide, using the figure below, estimate the number of polypeptide residues needed in an alpha helix to cross the membrane. Okay, so this is our transmembrane domain shown in this box, and this whole structure is an integral membrane protein. So we have parts that are cytosolic, okay, that point towards the inside of the cell. We have parts that are extracellular, which points on the outside of the cell. And then within the box, we have parts that span the span the nonpolar region of the lipid bilayer. So we call that the transmembrane domain, right? So how many residues are needed to cross once? Okay. Consider how to do this and then respond. And so pause if you need to. Okay, so we remember from our earlier chapter on the structure, right? We can estimate the number of residues by counting the number of loops in the helix. And so remember, the helix is what's spanning the nonpolar region of the lipid bilayer. And so we can say 1, 2, 3, 4, 5, about 6, right? So we have 6 loops times 3.6 amino acids per loop. And I get that to be about 21.6, so approximately 22 amino acids. Okay. And so the answer here is D. Okay. And so we can look at this and we say, okay, well, what we also know is that you have the thickness of the hydrophobic region. So again, if remember when we talked about, right, the what's interesting about these is that the most energetically favorable conformation in the lipid bilayer is to actually have the fatty acids stretched out as much as they can, if they can. So remember, unsaturated fatty acids can't really stretch out in the same way that saturated fatty acids can. But let's assume we're just talking about saturated fatty acids, and they can completely stretch out to the longest length that the fatty acid will allow. all right? And so the thickness of the nonpolar region of the lipid bilayer tends to equal, right, the size of the of when the fatty acids are completely stretched out on both sides of the bilayer. So remember, we have a set of fatty acids pointing with their fatty acid tails pointing inwards on one side of the bilayer, and then a second set there pointing inward this direction from this side of the bilayer, right? And so that ends up being about 3.5 nanometers. Okay, and so what that means is that this 20 to 25 residues that we just estimated here is sufficient to cover this 3.5 nanometers of the nonpolar region, or the hydrophobic region of the lipid bilayer. Okay, so knowing that, right, which of the following, so with all our discussion here, which of the following sequences is most likely to constitute a transmembrane domain? So look at the sequences provided here, A, B, C, and D, and decide which one you think would most likely be a transmembrane domain. Pause your video now to give it a shot and return when you're ready. Okay, the correct answer here is C, right? And so let's go through all of these and see why, all right? For with A, right, so remember we have two requirements. So let's start with B actually. So what's wrong with B? B is too short, right? So we just said we needed about 20 to 25 residues in order to span the transmembrane domain, all right? This is much too short to be a transmembrane domain, so we immediately can cancel this out, okay? But the rest of them are about the same length, so what is the difference between them, right? Well, now remember, we have, if these are alpha helices, that's great, okay? That allows it to be more likely to be a transmembrane domain. But then we have to think about the side chains, right? Side chains are going to stick out like spokes, right? Towards the hydrophobic region of the lipid bilayer. So what that means is that the residues largely need to be nonpolar, right? And therefore compatible with the nonpolar region of the lipid bilayer. If we look in this sequence here, we have histidine, right? Glutamate, lysine, arginine, glutamate, glutamate, aspartate, arginine, lysine, lysine. So in other words, a lot of potentially charged amino acids, which are not going to be compatible with the lipid bilayer, okay, the nonpolar region of the lipid bilayer. So we can cross this out. All right. With D, right, we have a similar situation, right? We can sit and look at this, and we can see several charged and polar amino acids incorporated into that. So we can cancel that out. All right, and C is the correct answer, because if you look, these are all largely nonpolar residues with nonpolar side chains, which would be compatible with the nonpolar region of the lipid bilayer. Okay. So for our last question, all right, which membrane protein type is most likely to have hydrophobic regions on its surface? Okay, so I'm asking is on the surface of the hydrophobic region. So let's say we have this integral membrane protein, for instance, right? We're talking about on the outside, right? So which one is most likely, all right, to have hydrophobic regions on its surface? Is it A, a peripheral membrane protein, B, a lipid linked, C, an integral membrane protein, D, B and C only, or E, all of these? Go ahead and pause your video now, consider it, answer, and then return when you're ready. Okay, the answer here is D, B and C, right? So let's go through all these. So a peripheral membrane protein, as the name suggests, hangs out on the periphery of the lipid membrane, okay? And so peripheral membrane proteins can actually be dissociated, often dissociated from the membrane protein, from the membrane, excuse me, by adding a solution of sodium chloride or some higher ionic strength solution. Because for peripheral membrane proteins, these are largely hanging on and associating with the charged head groups, charged or polar head groups of the lipids that are incorporated in the lipid bilayer. And so it's largely hydrogen bonding and electrostatic interactions that are holding the peripheral protein to the lipid bilayer. And so they're not actually incorporated within this nonpolar region of the lipid bilayer, okay? And so this is less likely to have hydrophobic regions on its surface. And in fact, it's more likely to have more charged residues on this side of the surface. And then what you would expect, a mixture of polar and charged residues on the side that is facing towards this, in this case, the cytoplasm. Okay, so that is incorrect. Okay, integral membrane proteins, we'll start here next because this is easy to see, right? Because this the integral membrane protein is required to span the membrane, right? It's required to have a transmembrane domain. And so here's another version of an integral membrane protein, right? With just a single alpha helix transmembrane domain. And so as we just discussed with the alpha helices, right, these side chains need to be hydrophobic. And so you expect to have hydrophobic regions on the surface of the alpha helix. And much in the same way in an integral membrane protein and a different type of integral membrane protein that has more than one alpha helix transmembrane domain or more complex transmembrane domain, you would expect a lot of hydrophobic patches. Hydrophobic regions, especially in the regions that are spanning the nonpolar region of the membrane. Okay, so that's correct, right? And then the lipid linked, right? So as the name suggests, there's these are covalently attached to some sort of lipid that is incorporated into the membrane, and there will also be some regions that might be pulled in there. For these lipid link proteins, right, they're going to be hydrophobic, and so you would expect that to have some hydrophobic regions as well. So of course the answer then is B and C only. Okay, thank you everyone. And if you have any questions, please feel free to email me. I'll have access to my email, and I will see you when I get back next Monday. Okay, take care.